Yeah, welcome. So today we'll be moving to the next topic, which is process synchronization. So we'll be discussing this topic under these headings. First, we'll be discussing the background, where we'll try to understand what is meant by process synchronization and why processes should be synchronized. If processes were not synchronized, then it will lead to a problem called as critical section problem. What is meant by critical section problem? We'll be discussing that with an example, and then we will be discussing the first solution that was given to a critical section problem, which is called as Peterson solution. So we'll understand how the Peterson solution works. Followed by that, we'll be discussing several other solutions for critical section problem, which were hardware based and software based. Okay, we'll be discussing some software based solutions like mutex locks, semaphores, and we'll be discussing few classical problems on synchronization, and we'll be ending the topic with a introduction to a concept called monitors, which is also uh, a solution to critical section problem. So the objective of this chapter is to introduce the concept of process synchronization. What is meant by process synchronization? What is its importance and why it should be done? And then we'll be discussing about critical section problem. That is, if processes were not synchronized, it will lead to a problem called critical section problem, and how this problem can be solved. We'll be discussing a generic solution to critical section problem, and then we'll be discussing several hardware and software based solution for critical section problem. And finally, we'll be discussing some classical synchronization problems. Okay. So let us move to the topic. So let us try to understand the need for process synchronization. So as we know already, processes can execute concurrently. Concurrently in the sense, the concurrently in the sense, the system is having only one CPU or one processor, but the processor can context switch between different processes. The processor can context switch between different processes. So that is what is called as concurrency. Okay. So concurrency is not parallel execution. So for parallel execution, you need more than one processor. Okay. So we know that processes can execute concurrently, and sometimes these concurrent processes may share a common data. Sometimes concurrent process may share a common data. And if two processes were sharing a common data item, and if they are executing concurrently, then it may lead to a problem called as data inconsistency. Then it may lead to a problem called as data inconsistency. That is, the data may be maybe in the wrong state after both the process got executed. Okay, so this problem is created because these concurrent processes were not synchronized. This problem is created because these concurrent processes were not synchronized. Concurrent process were also are also called as cooperative process. If two processes were executing concurrently, then they can also be called as cooperative process. So when there is a concurrent process or cooperative process running in the system, and if these processes were sharing a common data item, then the operating system should ensure that these processes were executing in a particular order. These processes were executing in a particular order. That is, they should not execute concurrently. They should follow some order. If there are two processes P1 and P2 and they are sharing a common data item K, then these two processes should not execute concurrently. If they execute concurrently, then it will lead to a process, then it will lead to a problem called as data inconsistency. To avoid data inconsistency or to ensure data consistency, The operating system should ensure the orderly execution of these processes. That is, either process 1 should execute first and then process 2, or process 2 should execute first and then process 1. Okay. So, so if these two processes were executing in an orderly way, then that is called as synchronized. Then these two processes are said to be synchronized. Because if they are not synchronized, and if they are accessing and if they are executing concurrently and if they are sharing a common data item, then it will lead to a problem called as data inconsistency. To ensure data consistency, these processes should execute in an orderly way. Okay, so if they execute in an orderly way, then that is called as, then they said to be synchronized, then the processes were said to be synchronized. We shall discuss this with an example. So let us consider a classical problem which is called as producer consumer problem. So, so producer consumer will be discussing how data inconsistency occurs with a producer consumer problem. So producer, so producer is a process, consumer is also a process. Okay, producer is a process and consumer is also a process. So we have two processes. One is called as producer and the other is called as consumer. So let us call producer as P and consumer as C. These two are processes. Okay. These two processes were sharing a common buffer. Okay, these two processes were sharing a common buffer. Let us assume the size of the buffer is 5. That is, this buffer can hold 5 data items. This buffer can hold 5 data items. So this is a buffer and this buffer is shared by both the processes. One is producer, the other one is consumer, and the size of the buffer is 5, that is it can hold 5 data items, and there is a variable called counter. There is a variable called counter, and this variable is also shared between both the processes, producer and consumer. Okay, initially this counter will be 0. Initially the value of the counter will be 0, which means that the buffer is empty. Initially the value of the counter will be 0, which means the buffer is empty. Now what is the job of the producer in the sense? Producer will produce some data item and it will keep it in the buffer. Producer will produce some data item and it will keep it in the buffer. Okay, so this is the job of the producer, and the job of the consumer is, it should take some data item from the buffer and it will use it and it will consume or it will process it. Okay, so as long as there is some space in the buffer, the producer will keep producing and it will be keeping in the buffer. So here the buffer size is 5. So before keeping any data item to the buffer, the producer should check what is the current capacity of the buffer, whether the buffer is already having 5 elements or not. If buffer is not having 5 data items, then the producer can add one more data to the buffer. Okay, at any location, whichever the location which is free, that producer will be keeping track. Okay, starting from 0th location, you can assume this is 0th location, this is first, this is second, this is third, and this is fourth. Okay, so producer will be keeping track of which location is empty. In that location it will keep the data item. Similarly, consumer will consume data items from the buffer. So before consuming, the consumer should check whether is there any data item is there in the buffer or not. If the buffer is empty, that is, if the buffer is not having any data item, then the consumer cannot consume. So as long as there is some data item, the consumer will keep consuming the data item. Okay. And this counter, what happens to this counter in the sense, whenever the producer produces some item and it places that item in the buffer, the producer will increment the counter by 1. Producer will increment the counter by 1. Whenever the producer creates some data item and if it adds it to the buffer, then the producer will increment the counter by 1. Okay. So remember, this counter is a shared variable. Similarly, whenever the consumer consumes some data item, the consumer will decrement the counter by 1. Okay. So whenever the producer produces an item, the producer will increment the counter by 1, and whenever the consumer consumes an data item, the consumer consume decrement the counter by 1, and this counter is a shared variable. Okay. Now let us discuss a problem where when if these producer and consumer were executing concurrently, if these two processes, producer and consumer, were executing concurrently, how it may lead to data inconsistency. Okay, how it may lead to data inconsistency. So here the shared variable is counter. So this shared variable counter may get inconsistent if they were allowed to run concurrently. So that we'll be discussing with an example. Okay. So this is the code for the producer. Okay, this is the code for the producer. So what this code says in the sense, while true, that is keep on continually doing this, what you should do, while counter is equal to buffer size. So, so here what is buffer size? In our example, buffer size is 5. Okay, initially, let us assume initially counter is 0. So counter is not equal to buffer size. If counter is equal to buffer size, then you can see there is a semicolon here, which means that loop will execute infinite number of times. Okay, that is, it will become an unending loop. Okay, so if counter is equal to buffer size, that is if counter is equal to 5, then it will keep on it will keep on checking this, and it will keep on waiting. That is, the process will not do anything. It will become an infinite loop, and once the counter becomes less than 5, then it will continue. Okay. So basically this statement says, if the buffer is full, then don't do anything, just wait. So if counter is equal to 5 means the buffer is full, then it will be just waiting with this infinite loop. Okay. If counter is not equal to 5, in our case, counter value is 0, which is not equal to 5. So it won't wait, it will come inside. Buffer of in is equal to next produced. Okay. So in will be initially 0. So in is a pointer which is maintained by producer. Similarly, out is a pointer which is maintained by consumer. These are not shared variable. These are local variables. In and out are local. In is local to producer and out is local to consumer. Okay. So buffer of in. So in will be initially 0. Buffer of in is equal to next produced. So that is buffer of 0. Whatever the item produced, that will be kept in this location. Okay. That will be kept in this location. In is equal to in plus 1 percentage buffer size. So that is, now in becomes 1. 1 modulo 5 is 1. Okay. So this modulo we are doing because after 5 it should again come back to 0 for that purpose. Okay. So, or after 4 it should again come back to 0. Okay. So in, currently in is 0, 0 plus 1 is 1, 1 modulo 5 is, the remainder is, again it will be 1. Okay. So now after executing this, in will become 1. So no more in is 0, now in is 1, and counter plus plus, and counter plus plus, that is counter will become 1. Counter will become 1. That is all, there is one item in the buffer. That is the meaning. So this is what the code of producer. So like that, the producer checks whether the counter is equal to buffer size or not. If the counter is equal to buffer size, then it means the buffer is full, so it will wait. Otherwise, it will add an item to the buffer. Okay. Similarly, if you see the consumer, this is the code for the consumer. Consumer, what it does in the sense, it checks whether counter is 0 or not. If counter is 0, then you can see there is a semicolon, which means this loop will become an infinite loop. It will keep on waiting, and it will keep on checking whether counter is 0 or not. As long as counter is 0, it will wait. The moment counter becomes 1, 2 or something, then it will come inside. Okay. So now we know previous case, based on the previous case, we know counter is 1. That is one item producer has added into the counter. Okay, so counter is not 0. So counter is not 0. As counter is not 0, it will come in. So then what it will do, next consumed is equal to buffer out. So out is a local variable which is maintained by the consumer. So initially out value will be 0. Okay. So what so this statement, what it does, next consumed is equal to buffer of out. That is, whatever in the zeroth location in the buffer, whatever the data item in the zeroth location in the buffer. So this item, that is X, is in the zeroth location. So that is now taken out. Okay, and that is the next consumed. So next consumed will be holding that item. And then it increments the out. Out is equal to out plus 1 percentage buffer. That is out becomes 1. No more out is 0, now out is 1. And counter minus minus, counter minus minus. Now counter will become what? Now counter becomes 0, because already producer produced only one item and it kept, and now counter becomes 0. Okay, now counter becomes 0. Now again it will go back and check, while now counter is 0, so it will just wait here. It will wait until producer produces something. Okay, so this is the code for producer and consumer. Okay, actually this code is correct. There is nothing wrong with the code. Programmatically it is correct, but still we are considering producer as a separate process, consumer as a separate process. Now if these two processes were allowed to run parallelly, then this may lead to a problem, and that problem is called as data inconsistency. So how it will lead to data inconsistency, that now we'll be discussing. So we know that this counter is a shared variable which is shared between producer and the consumer. Okay, now so this counter plus plus is a statement which is added in producer. Counter plus plus is a statement which is added in producer. Okay, so this is similar to a C statement or a C plus plus statement. But internally, when it is executed by the process by the processor, this won't be executed as one single statement. This statement may be split into multiple statements. This single statement counter plus plus, it won't execute as one single statement, rather it will be split into multiple statement. So probably this statement will be split something like this. Okay, so that is, so when the processor executes this, it won't execute it as a one single statement. It will execute this single statement as three different statements. So first the processor, what it will do in the sense, it will store the value of the counter in some register, in some general purpose register. Then it will increment the value of the register, that particular register, by 1. After incrementing, then again it will store the value of the register to the counter. Okay. Similarly, when counter minus minus, this statement is in consumer. Similarly, when consumer executes counter minus minus, this is basically in a high level language, it is given as a one single statement. But when the CPU actually executes, this statement also may be splitted into three different statements like this. So CPU will be executing this as a three different statements like this. So first the CPU or the processor, what it will do in the sense, it will store the counter value in some other register, register 2, and then it will decrement that particular register, and then whatever the current value of that register, that will be stored in counter 2. Okay, so now these two are, even though they are single statement in producer and consumer, but actually when it is implemented, these are implemented as three different statements. Okay, and now if these two processes are running concurrently, this may lead to a data inconsistency problem. How it occurs, that we'll discuss with an example. Okay, so now consider this. Assume initially, so this is the sequence of execution. So assume this is the first statement that that got executed. This is the first statement that got executed. Okay, so that is producer is executing register 1 is equal to counter. Producer is executing register 1 is equal to counter. Let us assume initially the counter value is 5. Let us assume initially the counter value is 5. Okay, so now producer is executing register 1 is equal to count. So now what happens at this point, register 1 contains 5. Again, then producer is executing register 1 equal to register 1 plus 1. So now register 1 becomes 6. Okay, so that is initially producer is executing these two statements continuously. After that, there is a context switch. After that, there is a context switch, and then consumer is executing two statements. Then consumer is executing two statements. So first consumer is executing register 2 is equal to counter. Still counter is not updated, you see, because counter is 5 only. It has not yet updated the counter. Okay, even though producer has incremented the register, it has not updated in the counter. So register, so currently counter value is 5. So register 2 contains 5. And then consumer executes register 2 equal to register 2 minus 1. So now register 2 becomes 4. Okay. Then again, then then there is a context switch, and now producer is executing. Now producer is executing, and it is storing the content of register 1 to counter. It is storing the content of register 1 to counter. So in the producer code, what is the value of register 1? 6. So it is storing 6 to counter. Okay. After that, there is a context switch, and consumer is executing, and consumer is executing, and consumer is storing the content of register 2 to counter. The content of register 2 is 4. So it is storing 4 to counter. Okay. So finally, when all these 6 statements were executed in this order of interleaving means in one order of context switching. In this order of interleaving, the counter contains the value 4, which is not correct. It is not correct. This is inconsistent data, because as a whole there is one increment and one decrement, and initially it is 5. Okay, so in any order, if you execute, you are incrementing and then decrementing, so it should become 6 and 5. Okay, or if you are decrementing and incrementing, it should become 4 and 5. It is finally it should be 5. That is the correct answer, but here it is becoming 4. Okay, so this is one order of interleaving. Similarly, there may be other order of interleaving also. Okay, so it may sometimes, so here it ended with 4. If the interleaving order is changed, this may end up with a value 6 also. This may end up with a value 6 also. Assume that assume that this is the first statement got executed. Okay, and this is the second statement got executed. Everything is the same, and this is the third statement got executed, and this is the fourth statement got executed, and this is the fifth statement got executed. Okay, this is the fifth statement got executed. So when executing the fifth statement, counter value will be 4. And assume this is the last statement got executed. That is, after S3, there is no context switch. This is executing. So let us assume this is S4. I mean, this is S4 and this is S5. Okay. After executing S4, there is a context switch. Then what? Then what will happen? Then counter will end up with a value 6. Again, this is also inconsistent. Again, this is also inconsistent. Okay. So there are, so basically uh, this particular if you allow concurrent execution, this particular case, this particular statement can produce three results. Either if counter is equal to 5, either it can produce a result 4. So this is what we have discussed for 4. Okay, so if these two are interchanged, that is, if this is executed first and if this is executed next, then instead of 4, it may create 6. It may create 6. 4 is also wrong answer, 6 is also wrong answer. But if they follow some other order, it may create 5. That is a correct answer. But we don't know processor will follow which order. Okay, so in which order it will create 5? In which order it will create 5? In which order? In the sense, say after executing these two statements, say producer is not context switching, then it is executing this statement. Okay, then it is executing this statement. So this is S2. If this is S2, okay, if this is S2, sorry, not this. Okay, not this. So after executing these two statements, the producer is not context switching. Rather it is executing this particular statement. This particular statement. So it means this statement becomes S2. Okay. So here register 1 is counter, which is 5. Then register 1 equal to register 1 plus 1, which is 6. Then counter equal to register 1. So now counter will be what? Now counter will be 6. Now counter will be 6. Okay, that is counter value is now 6. Okay. So after this, if this executes, so if this particular statement executes after this, That is, if this becomes S3, that is, this is 0, this is first statement and this is second statement. So now counter is updated to 6. After that, this statement is executing. So register 2 equal to counter. What is counter? 6. So now register 2 will be 6. Okay. Then it executes this statement. Register 2 equal to register 2 minus 1. That is, register 2 is 6. 6 minus 1 becomes 5. 5. Okay. And at last, it executes this particular statement. Okay, so that is, this is S2, this is S3, this is S4, and S5 is correct. Now now register 2 value is what? 5. So register 2 is stored to counter, so that is, counter will be holding the value 5. Okay, so in that case, it will be correct, but we don't know in which order these processes are going to execute. Okay, so there are lot of chances for the data getting inconsistent. Okay, so this is the problem that happens if multiple processes that were sharing the common data item were allowed to execute concurrently. Okay, so let us stop here and we will continue this from the next session. So what we have discussed, in the sense, we have discussed the introduction to process synchronization and the need for process synchronization. If processes were not synchronized and if they are sharing the common data item, then it may lead to a problem called data inconsistency, and we have discussed that with an example using producer consumer